All right, so the bottom left, we have 2 plus I on top and 1 minus I on the bottom. The bottom is what matters. We have a complex number on the bottom, so that means we're going to have to multiply by what? The complex conjugate of the denominator, which is 1 plus I. And this is going to be a fancy one, so 1 plus I on the bottom, 1 plus I, that's an I, on the top. Now, we're going to FOIL on the bottom, but we know that it's a complex conjugate on the bottom, so the O term and the I term are going to add to 0. On the top, how are we going to multiply those? That is also FOIL, but those are not complex conjugates. So when we FOIL, the O and the I terms are not going to add to 0, okay? So don't get so shortcut happy that you accidentally only multiply the F terms and the L terms in FOIL, okay? This is FOIL as well, top and bottom. So let's go ahead and FOIL the bottom. We know the O and the I terms are going to add to 0, so I'm not even going to mess with them. What do we get on the bottom? We get 1, and then minus I squared, but I squared is negative 1, so minus negative 1 becomes plus 1. So we have 1 plus 1 on the bottom. That's nice. Now up top, FOIL that. What do we get? 2. Okay, plus 2I. No. Plus I. We're FOILing. Plus I squared, which is going to be minus 1, because I squared is negative 1, so we have minus 1. So now combine those. So on the bottom is really just 2. On the top, we have, do the real part first, so 1 plus 3I. Right. Now let's fix this so that it's correct as far as complex number is concerned. 1/2 plus 3/2 I. And you're done. See, it's not really that bad, right? As long as you learn what it is that you're supposed to do first. The toughest part of the problem really is the FOILing part.
Why is it 1 plus 3i?
1 plus 3i. 2 and negative 1 becomes 1. And then 2i plus I is really 2i plus 1i, which is 3i. Okay? Now this fourth one here is kind of a spin or a take on the one above it. Okay? We have a complex number on the bottom, and then something that's not quite a complex number on the top. All right? So we know that we're going to need to get rid of the imaginary part on the bottom by doing what? So a fancy one is going to be what?
3 minus 5i.
Okay. But what's different about this problem as opposed to the one above it?
It's already
We have the negative out front. Okay? So the problem with this is, what do we do with that negative sign? Okay? Okay, so that is one of the options. We could save it for later. But the problem with that option is, if you're the type of student who constantly leaves negative signs off, you're probably going to forget that you saved your negative sign for later, and you're going to leave that negative sign off, and now you got the answer wrong. Okay? You could apply the negative sign to the top, or you could apply the negative sign to the bottom, but you don't apply the negative sign to both the top and the bottom. Okay? So if you think maybe I'll apply the negative sign to the bottom, if you're the type of student who doesn't really get the idea of distributing the negative sign in, and you constantly are you're getting like the negative sign in the first term, but not all the terms, then you're probably going to screw this up and you're not going to get the right answer. Okay? So my advice to you would not to be to leave the negative sign off until the end. It would be to apply the negative sign to the top and deal with it right now. That's what I would do if it was me doing this problem. And it is me doing this problem, so I guess that's what we're doing. So the complex conjugate is 3 minus 5i. Then you would have negative 3 minus 5i to start. And then your complex conjugate would be negative 3 plus 5i. But that's not what we're doing. We're doing this. This is easier. Okay, now, what? Foil on the bottom, so what's the bottom?
9.
So minus 25i squared becomes plus 25 on the bottom. And then how am I doing the top? Distribute. So I have negative 2i times 3,
Wait, how come we didn't do the
negative 6i. And then, so plus 10i squared becomes minus 10. Okay, now?
at the bottom?
So the bottom is 34. And the top, I should write what? Yeah, negative 10 minus 6i. Okay, now let's make this an answer. Okay, negative 10 over 34 should be what?
Negative 5 over
17. Okay, good. And then?
minus, or
It is minus.
negative.
Okay, but 6 over 34, those are both even. I'm dividing by 2, though.
3.
Yeah, 3 over 17. Don't forget the I. There's your answer. So here's a real-world example on a profession that might use this type of math. If you were an electrical engineer, or if you were in college going to study to be an engineer of any kind, you're probably going to wind up taking an electrical engineering type of class. And eventually you'll study circuitry and find out that this type of math that you're learning right now applies to electricity. The voltage V in a circuit is defined by V equals CI, where C is the current, which is measured in amps, so capital A for amps, and I is the impedance, which is measured in ohms, and that symbol right there is the Greek letter omega. Kind of looks like a wig to me, but if you were to look at the back of a speaker, on the label on the back of a speaker, you would see that symbol, and it's actually telling you about the resistance on that speaker, okay, the impedance. I'm sure there was. So in a particular circuit, the voltage is given to you as 20 minus 12J volts, and the impedance is 6 minus 4J ohms. And what you need to know is this J that you're looking at acts just like the I that you've been studying in complex numbers. J is a complex number just like I is. J is defined as the square root of negative 1. Okay? What is the current? Well, what we do is we take this equation, V equals CI. If my board decides to work, there we go. V equals CI. And since we're looking for the current, it says, I'm going to solve this equation for current by dividing both sides by I. So I have C equals V over I. And now they told me that the voltage is 20 minus 12J. And they told me that the impedance is 6 minus 4J. So what do?
Well, your J is going to be like your I.
J is just like the I. And I got a problem. I got to get rid of that J in the denominator. So we're going to multiply by the complex conjugate. That's right. So multiply by what? 6 plus 4J. And so FOIL, yep. So we have equals now because it is an equation. What do I have in my denominator? Okay, 36 minus 16J squared, but that would become plus 16. Okay, now J is acting just like I. So J squared is negative 1. The numerator is what? 120. minus 80j or plus 80j. Yeah, it's plus. And then minus 72j. And finally, minus 48j squared, which becomes plus 48. Okay. What's the bottom? 52. And then on top, we have 120 plus 48, 168. And then 80j minus 72j plus 8j. Now we just got to make that look right. What is 168 over 52? So 42 over 13, and then it's going to be a plus. What?
4 over 26.
Those are both even. That's definitely going to reduce again.
2 over 13.
2 over 13, that it? J. There's your answer. And now you're acting like electrical engineers. Congratulations. Okay, so next is the complex plane. I always look forward to this one. I think it's kind of fun. The complex plane is just like the coordinate plane, except it's using complex numbers. We can graph complex numbers as points in the complex plane. This plane has a couple major differences, though. Instead of x and y like we have in the coordinate plane, the real part of the complex number takes on the x-axis, and the imaginary part of the complex number takes on the y-axis. So then the complex number itself, the real part of the complex number, acts like the x-coordinate of the ordered pair, and the imaginary part of the complex number acts like the y-coordinate of the ordered pair. And then you can plot those as points on the complex plane. Okay? And then if you look at step 4 down there, number 4, the absolute value of a number is its distance from 0. We've talked about that quite a bit. So how do we figure out how far from 0 a complex number is? It's the same thing. How far away from 0, from the origin, is the point that we plot in the coordinate plane. That straight line distance from the origin to the point that we plot in the coordinate plane is its absolute value. Okay? So we're going to use negative 5 plus 3i as an example. So first let's plot it to find out where it is on the the complex plane. Negative 5 is the real part, so we go to negative 5 on the real axis. That's left 5. And then 3i is the imaginary part, so we go up 3. So negative 5 on the real axis, and then up 3. Here we are at negative 5 plus 3i. It acts just like an ordered pair, negative 5 comma 3. Okay? Now, what is its absolute value? Again, its absolute value is going to be its straight line distance from the origin to that point. Okay? So its straight line distance means from the point to the origin, it's that length right there. Okay? How do we calculate that distance? It's not slope.
Should we draw that line?
Can we use the Pythagorean theorem? Sure we can. We can also use the distance formula, but guess what? They both are the same.
Should I draw that?
Yes, the distance formula is the same thing as the Pythagorean theorem. It is. You've been doing them both for forever because they're the same thing. So if I draw a triangle on here, the Pythagorean theorem says if I have a right triangle, then what?
A squared plus B squared
A squared plus B squared equals
equals
C squared. Now, what side of the right triangle do I have here that I'm looking for? I'm looking for not c squared, but c. I'm looking for the hypotenuse, c. Okay? Pythagorean theorem says a squared plus b squared equals c squared. So if I want c, what do I have to do to this formula? I have to square root both sides, right? So that means I'm looking for c equals the square root of a squared plus b squared, right? That's what I need to use. So let's talk about the distance formula for a second. Does anybody remember the distance formula? No. Nobody remembers the distance formula, right? Because it's way too complicated and probably somebody somewhere along the way let you just use a cheat sheet so you didn't have to memorize it. That wasn't me. D equals the square root of, no, x2 minus x1 squared plus y2 minus y1 squared. No, that's the distance formula. No, it's the distance formula. Well, guess what? What is this length right here on this problem? 5? How'd you get that? Because you counted it? Because the length of that line segment is 5. How do I know it's 5? Because our point is over there at -5 from the origin. How long is this right here? 3. How do I know it's 3? Because I went 3 up from the x-axis, right? From the real axis. Well, guess what? No, you're right. But x2 minus x1 says this minus this. And all that does is give me the length of this segment right here, which you guys told me already was 5. And how did you know it was 5? Shh. How did you know it was 5? Because you counted it. And y2 minus y1 gives me this distance right here because all I'm doing is I'm subtracting this number from this number. So all you're doing is you're giving me the length of this leg here, and you're giving me the length of this leg here. But the length of this leg here is the same as that one right there. So A is actually x2 minus x1. And what am I doing to A? I got to square it. What am I doing to this? I'm squaring it. And this is nothing more than the length of this leg, which is B. What am I doing to B? I'm squaring it. How do I calculate the length of this leg? I do y2 minus y1. What am I doing to the length of that leg? I'm squaring it. What is the distance formula? It's the length of the hypotenuse in the Pythagorean theorem. The distance formula is nothing more than the Pythagorean theorem. You guys have been doing the Pythagorean theorem and the distance formula together for forever. The distance formula doesn't suck. It's the Pythagorean theorem. You just never saw it before. Nobody ever told you that. How does it help you? You can now find the absolute value. You can find the length of this segment using the Pythagorean theorem or the distance formula. It doesn't matter. Just let me teach it. Let me teach it. Find the absolute value of the number. So we have absolute value, -5 plus 3i. Okay? The distance from 0 is the square root of the length of one leg squared, so 5 squared, plus the length of the other leg squared, 3 squared. So we have the square root of course, 25 plus 9. So that is the square root of 34. And we need to simplify that if it simplifies. The only factors of 34 are 2 and 17. Both are prime. Neither one is a perfect square. So that's it. The length of that segment from the end point to end point is the square root of 34, and that's it. That's the absolute value of -5 plus 3i. Now, we have a bunch of examples here. We're going to practice.
All on the same graph?
All on the same graph. And on the homework, it's going to ask you to do this. Do them all on the same graph. -5 minus I. Where do I go? Right 5 and then down 1. Mark it, label it. 5 minus I. Next one. -3 minus 2i. Where do I go? Left 3 and then Down 2. Mark it. Label it. Negative 3 minus 2i. Next one. 1 plus 4i. Where do I go? Right 1, up 4. Mark it. And label it. Okay. Negative 1 plus 3i. Where do I go? Left 1, up 3. Mark it. Label it. Okay. Negative 6i. Just down 6. Right there. Negative 6i. And finally, negative 4. Left 4. Mark it. Label it. Again, this is the real axis. This is the imaginary axis. We're going to connect the dots. So, from the origin to 5 minus I makes that segment right there. What is the distance, the absolute value, the distance from the origin to 5 minus I? Well, that's going to be the square root of 5 squared, which is 25, plus negative 1 squared, which is 1. You get the square root of 26. Does that simplify? No. So the square root of 26 is the absolute value of that complex number. What's the next one? Negative 3 minus 2i. Square root of 9 plus 4, which is square root of 13. 13 is prime, so that definitely doesn't simplify. Okay, next one. 1 plus 4i, so the absolute value will be square root of 1 plus 16. So square root 17. Again, prime does not simplify. Okay? Negative 1 plus 3i. The absolute value of that will be what? Square root of 1 plus 9, which is square root 10. Does that one simplify? Nope. Those are factors. Neither one is a perfect square, though. Does not simplify. Okay, how about the negative 6i? That's a straight line shot. It's a vertical distance from the origin to negative 6i. It's just a distance of 6. Hopefully that one logically makes sense. How about negative 4? Yeah, that's just 4. We're running along an axis.
So even if it has a negative, it's going to be positive?
Factoring using complex conjugates. So I have to say that what we're looking at here on this top row, x squared plus 81, for the first example, does not factor. Okay? That is the sum of squares. If it was x squared minus 81, that would be the difference of squares, and the difference of squares does factor. X squared plus 81 does not factor. Okay? What we're doing here is we're seeing that we can use complex conjugates to kind of say that it maybe can be factored if we use complex conjugates. But in reality, x squared plus 81 is the sum of squares, and the sum of squares does not factor. Okay? I don't want you guys to get the wrong idea into thinking that this does factor, because it does not. Okay? So as I say, you actually can factor things that seem to not be factorable using complex conjugates. You can't, but we're going to. Okay? What have we been doing in this section?
Stuff that you can't do.
We've been doing things you can't do. Okay? We've been working with imaginary numbers. We've been working with things that don't exist. So don't get the wrong idea. This whole section doesn't exist. All right? We've been working with things that don't exist. This also doesn't exist. But we can work with it. Okay? So we can use complex conjugates to factor x squared plus 81. If this was x squared minus 81, we would have no problem factoring this into conjugates. We would have plus and minus.
Is that what we're doing?
Yep. And then we would have the square root of x squared, x and x. And then we would have the square root of 81, which is 9. but this is going to be complex conjugates to make this actually work. So it's going to be 9i and negative 9i. Okay? Does this factor? No, it doesn't factor. But we're going to use complex conjugates to make it look like it factors. Okay? If I FOIL this back out, because these are complex conjugates, the O term and the I term in FOIL disappear, and I'll be left with x squared. X times x is x squared, and 9i times negative 9i is negative 81i squared. I squared is negative 1, so negative 81 times negative 1 is positive 81, and we're left with x squared plus 81. Okay? So the second one, 5x squared plus 20, what's the first thing we do? What's the first thing we do? We can't divide because this is not an equation, but we can factor out a GCF of 5. What's left over? X squared plus 4. Now, technically, we should be done here. This does not factor. However, in the spirit of doing things we're not able to do, we're going to factor it anyway using complex conjugates. So 5, and then break it into a FOIL problem. Plus and minus x 2i and good. Actually not good, it's terrible, but that's what we're doing. Okay, and the last one. Take out the 2, it's a GCF. What's left over? 16, right? And then? Don't forget your GCF. 4i, x minus 4. Don't forget we're square rooting. Okay, good. Now, I have a new equation on here that I need you guys to write down. X to the 4th minus 16. And we're going to factor this guy.
Just write it down anywhere.
Yeah, just wherever there's space.
Wait, so what's the point of this? If we're just...
Does x to the 4th minus 16 factor?
Yeah.
Yes. This is the difference of squares, right? Is x to the 4th a perfect square? Yeah. What times itself gives you x to the 4th? X squared times x squared is x to the 4th. So this actually does factor. So let's factor it. We're undoing FOIL. Plus minus, because this is the difference of squares. And what do I have? Yeah? Plus 4. Nope. This actually does factor. X squared minus 4. Okay, good. But we're not done.
Because you got to take out the square.
Because we can still factor this.
It's x
Okay?
minus-
Now,
x plus 2 and x minus.
does x squared plus 4 factor?
Yes.
No, it doesn't. But we're going to factor it anyway. Does x squared minus 4 factor? Yes, it does. This one does factor because the sum of squares does not factor, but the difference of squares does factor. But we're going to factor the sum of squares anyway because we're in this section. Okay, so x squared plus 4 factors into what? X plus 2i, good, and correct. Now x squared minus 4 factors, and it actually does factor, into x plus 2 times x minus 2. Good. Now it's factored, okay? So now let me ask you guys something. If this was an equation in the first place, okay, and we wanted to solve, meaning find where the graph crosses the x-axis, okay? So I have x to the 4th minus 16 equals 0. And I just factored it like this. So now all of these things equals 0. What would I do next? I got to solve for x. How do I do that? No. Nope. How do I get x by itself? I got all these factors equals 0. I have stuff times stuff times stuff times stuff equals 0. What do I do? No.
It's 0. If it equals 0?
I have something times something equals 0. What do I do?
Oh, you separate them out?
Zero product property. Well, here I got a bunch of stuff All multiplied together equals 0. So yes, you break all of these apart using the zero product property. Okay? Now, I will get from this one here, x equals 2. From this one, I get x equals negative 2. From this one, I get x equals 2i, and this one, x equals negative 2i. What does this mean? X equals 2i and x equals negative 2i.
That's where cross is.
You're going to see it cross the x-axis at x equals 2i and x equals negative 2i? Because they're imaginary. That's right. So how many times do I see this thing cross the x-axis? Only twice. Okay? And so that explains why, when we were dealing with how many solutions do we have for this parabola, and you had to say no real solutions, there were solutions. They were just what?
Imaginary.
They were imaginary. That's right. So that's what's coming. When we come back from Christmas break, we're going to be dealing with polynomials, not just quadratic equations, but polynomials that have both real solutions and imaginary solutions. And we're going to have to find all of them.
So how do you derive it?
So you now finally are able to use the quadratic formula under any circumstances to find solutions to any quadratic equation, whether they're real or imaginary. So these are the examples that we're going to do. Solve using the quadratic formula, okay? I want to at least get 2 of these done. So let's do the one on the far right first, because this one I like the best. So quadratic formula, x equals what? So negative 4 becomes 4. Plus or minus the square root of b squared, so 16, minus 4 times a, which is 1, times c, which is 5, all divided by 2 times a, which is 1, so 2. And then you simplify. X equals 4 plus or minus the square root of. Now, negative 4 times 1 times 5 is negative 20. So we have 16 minus 20, which is negative 4. So we have square root negative 4. Previously, that'd be it. You'd be like, no solution, right? But now we know. So we can do x equals 4 plus or minus, what is the square root of negative 4? 2i over 2. And now we like it to be the real part plus or minus the imaginary part. So we're going to break this apart. We have 4 over 2 plus or minus 2 over 2i. Those will reduce. X equals 4 over 2 is 2, plus or minus 2 over 2 is 1, I.
I don't like this approach.
We have time. Let's get the first one done as well.
This is just a different way of doing this.
Quadratic formula on the first one, quickly. X equals 3 plus or minus square root 9 minus 4 times a, 2 times c, 5. So 2 times a, 4. So x equals 3 plus or minus square root. 4 times 2 times 5 is 40. 9 minus 40 is 31. But it's negative over 4. Now 31 does not simplify, but the negative 31 does. So x equals 3 plus or minus square root 31 times negative 1 over 4. So this is 3 plus or minus square root 31i over 4. And then we just got to break that into the format we like. X equals, 3/4 plus or minus square root 31/4 I. Okay, we just made it. The section's over. We'll skip the middle problem. It's just like the first problem. Make sure you get this one done.